Hi, I'm Randall Heyman, a mathematics academic. Many students' learning will be impacted by the coronavirus. So if you'd like me to do a video for you or your students, please put a comment below the video and I'll try and help you out. Okay, we're doing this video on algebraic fields. So what's the concept of a field? We've already discussed groups and rings. So I've put this little map up, or table up, which I think will be a basis that we can go through things. So what I've tried to put here so far is what we had for rings. So I suppose if we first go back to groups, we said with groups, we have this operation addition and we have closure. We may have commutativity, in which case we call it an abelian group or a commutative group, which just means we can change the order of the addition. We definitely have to have associativity, which means if we're adding three of them, it doesn't matter whether we add the first and the second first or the second and the third first. We talked about we said we have to have an identity element. This is an element, often like 0, where if you add it on to any element, it doesn't change the element. And there has to be an inverse. So for every element, there has to be another element. When you add the two together, you get the identity element. So this bit here was what we had for groups. Then we went on to rings and we said, okay, well, you're going to add another operation, which we generally call multiplication. You definitely have to have closure. In other words, if you multiply two elements of the ring, it must still be in the ring. We didn't say anything about commutativity. We said you had to have associativity. We then went on and said, actually down the bottom here, distributivity. I've put it in the middle because it's that one, remember, that's a combination of the interactions between addition and multiplication. So we said things like, if you have A times B plus C, it must equal A dot B plus A dot C. And if you have A plus B dot C, it must equal A dot C plus B dot C. So I've put it down the bottom because it incorporates both multiplication and addition. Okay, so for a field, we need to start ticking more boxes. So the first thing we need to do is we're going to require it to be an abelian group or a commutative ring. Eventually, when you get a ring, whatever, it's got to be commutative. On addition, also has to be commutative for multiplication. We will work, remember we said there are rings and there are rings with identity, so we certainly need a ring with identity. We also need the inverse, that's important. So if you think about the integers, there is no inverse generally. So the inverse of 2 in our world is a half, but a half is not an integer. So there's no inverse generally in the integers. There is in the reals. And so for fields, we require an inverse. So there we go. That's all the conditions we basically need for a field. So they're all concepts that you're familiar with from the previous videos I've done. It's just a question that fields have to have them all. So what are some examples? Well, I suppose the rationals, there's inverses for rationals, satisfies all these conditions. The reals, the complex numbers, and then you have ones like I've mentioned now in more than one video, this sort of thing, A plus B root, let's make it root 7 this time, where A and B are, say, real numbers, could be complex, whatever, and normal addition and multiplication. So that would be a field as well. But the important point here is that when it comes to integers, definitely not a field because of this condition here, inverse. Doesn't have an inverse. So I hope that's helped with fields. We're heading towards quotient fields. So I'll see you for the next video. If you've got any questions about fields or anything else in mathematics, like me to do a video, comment below in the video. comment below this video, or in fact, comment below any video of mine, and I'll see it. Thanks very much.